So, the primary concern was whether the forces of constraint are always perpendicular to the displacement direction. It turns out that for holonomic plus scleronomic constraints, this is in general true. So, whenever we have a displacement of the system, let us say this is our system, could be anything. Whenever it displaces, the displacement is always perpendicular to the forces of constraint. It could be a bob of a pendulum, it could be a ball, an object which is sliding, it could be what other examples did we give? It could be other systems. We will see, we will take up some examples and we will see. So, wherever it is, if this is the direction of displacement r and this is the forces of constraint F c say. Okay. So, it is always seen that r perpendicular to F c for this case, for a holonomic and scleronomic constraint. By the way, this spelling is correct. So, it's SCLERONOMIC. Okay. Now, if we have holonomic plus rheonomic, that means when the constraint is changing, the condition of constraint is changing as a function of temperature. So, the example we gave was the following. So, we have let us say there is a pulley here and as a pendulum, other end of the thread. So, this is the thread of the pendulum which has a length L. So, the pendulum at this point, let us say it should move on the circle of radius L, right. But now, this side we have some extra thread and we can either release it or we can pull it little bit more, because there is, it is a pulley, let us say it is a frictionless pulley. So, it will not offer any friction to the system, but it will change the length as we pull on this direction or release in that direction, it will change the length. So, L is a function of t. So, if let us say the length is shortening and the pendulum is moving in this direction. So, as the length shortens on its passage, during this passage, it will end up here, not on this, but on a shorter path. Now, this, so the path is actually something like this. So, the direction of velocity at any instantaneous position is a tangent to the path, which will not be perpendicular to this direction. So, the tension T is always towards the center or the point of suspension, let us say, which will also slightly change, but if we, as it moves along the pulley, but let us assume that it is not changing, but this point is fixed, but what the main point is the velocity, which is the direction of instantaneous velocity, which is tangent to the path, is not perpendicular. So, this angle is not 90 degree, but something else. So, in that case we cannot say this, and the work done due to the forces of constraint, which is given by dW equal to F, we will write it as F c, yeah, F c dot dr, yeah. So, this is not, is in this case this is equal to 0, but if we calculate the same quantity for a holonomic plus rheonomic constraint, then dW, which is F c dot dr, is not equal to 0, because r is not perpendicular to F c, or I should not say r actually, I should say the velocity, instantaneous velocity v. In this case, it so happens that the velocity and no, I should not write r, because r has a different meaning. It is a displacement. I do not know how should I write it. For a pendulum, the displacement should be given by, okay, let us write it r only, just to be convenient. Just keep in mind that this r is not the length of the radial vector, but it is the displacement from the equilibrium position. So, we can use r. So, this is not generally true, that it is not perpendicular for holonomic and rheonomic constraint when the length, for example, the length of the pendulum changing. But also we have discussed a case where let us say this is a plane which is inclined and this object is bound to move on this plane, right. So, here also we see that this object is always the tangent, the normal force is always perpendicular to the direction of deviation. Now, as we change the angle, let us say the constraint condition is the plane equation. Now, if the plane is rotating, even if the plane rotates, the instantaneous displacement direction stays perpendicular. So, this is an example, it is a different type of system, but which is not true for this one. Now, so we can have, so what I am trying to tell you that we can have systems which are holonomic and rheonomic in nature, the constraints, where this is true. That means, the force of constraint and displacement, they are not mutually perpendicular. So, we can have non-zero work by the force of constraint. But we want to make the work done due to force of constraint uniformly 0 across all holonomic systems. That is our goal. Why and why will it necessary and how will it help us, we will see very soon. Now, in order to do that, we employ something, the concept of virtual displacement. Okay. And associated with this concept of virtual displacement is virtual work. First of all, what is virtual displacement? Virtual displacement is a concept which is very much used in the Lagrangian formulation of mechanics, and it is sometimes not so easy to understand. So, that is why I would like you to not necessarily, I always know that you are paying attention. So, that is not the problem, but the problem is if you do not understand what I am trying to say right now, you should not give up, but you should consult other books, you should consult other materials, you can always write to me, because this is a concept which is little difficult to digest. So, the situation is following. Virtual displacement is first of all, why it is virtual? Because virtual displacement, there is no passage of time during a virtual displacement. So, if I have to define virtual displacement, I would say it is the displacement consistent with constraint forces. Okay. That is one part of it, and the second part will be, so this part 1 and there is a second part. Part 2 is there is no passage of time. So, what I mean by these two statements are, first one is pretty much consistent, I guess we will all understand this, which displacement which is consistent with the constraint forces. That means, the displacements which are allowed by the constraint forces. Anyway, that is the case. I mean, even if the pendulum is moving in this particular path, that means this is because the length of the length is changing, length of the thread is changing, and length of the thread is changing. Length of the thread is changing means the constraint conditions are changing. So, depending on the constraint condition, it will choose its path. There is no problem with it. The second part is there is no passage of time, and that is why it is called virtual. So, it is not a real displacement to begin with. What I mean is, let us assume that, again let us go back to the pendulum. Let us assume this is the pendulum with length, which is a function of time at any instantaneous time point t, right. So, at at this time, if we assume a situation where time stops here. Okay. So, it's a bit difficult to understand. So, we are assuming that actually there is no time passage of time, no time elapsed, but we are assuming there is a small displacement which has to be keeping this equal to constant, which has to take place keeping this equal to constant, because L changes as a function of time, and because there is no passage of time, during that displacement L remains virtually constant. What I mean is, if I draw a circle of radius L, in actual situation, because L is a function of time, I have shown you already that the bob will not traverse along this path, along this circular path, but it will deviate from it. But if I am assuming that time is not elapsed during a displacement, that means length, which is a function of time, remains unchanged. So, it has to follow this path. So, if I have a displacement delta L, please remember that we use this curly symbol to make it separate from the real displacement dl. So, dl and delta L, they are not the same for a holonomic and rheonomic system. For systems where there is no, the force of constraint is not dependent on time, delta L is equal to dl. But in this case, delta L is not equal to dl, delta L is virtual, whereas dl is real. Okay. So, this is real and this is virtual. So, this dl, or rather delta L, is always perpendicular to the force of constraint, because T is this, and because L is not changing, L of T is constant, because we are, whatever we are considering, there is no time passage. So, that is why this delta L and T, which is along L, is always perpendicular. Okay. So, that is the beauty of virtual displacement. By introducing virtual displacement, we can always make, even for a rheonomic system, we can always make the work done due to force of constraint equal to 0. So, if we now try to calculate the work done for this system, which is called the virtual work, which is given by once again delta omega, which is F c dot delta L. What is the direction? Okay, by the way, these are vector quantities. Delta L and dl, these are all vector quantities. Okay. Could be vector, could be scalar, because we can also break it into components. Every vector has in the 3D world, it has 3 components. So, if curly delta L is a vector, then it will have 3 components, 3 x, y and z component, each we can write with a curly symbol. So, what I mean is, delta L vector is essentially delta x, delta y, delta z, where these 3 are the virtual displacements in 3 different directions. But anyway, it is not very important to break the equation here, but what we understand directly, that f of c is nothing but your tension T, and T is along L, and L and dl, they are of course perpendicular to each other. So, this is equal to 0. So, now what we did here, please understand carefully. What we have done here, we have constructed a system where, or we have constructed a virtual displacement which is at par to the forces of constraint, and because there is no passage of time, at that instantaneous time, at any instantaneous time, that particular moment forces of constraint has to be perpendicular to the direction of displacement. So, these two properties combined, a virtual displacement always produce a virtual work which is equal to 0. Right. Now, with this construction, and please remember, for a scleronomic system, so where the constraint condition is not changing, we do not need to worry about virtual displacements anymore, because in that case delta L is equal to dl. Okay. But using this delta L formalism, what we have done is, we have included all holonomic systems. Okay. When we are writing virtual displacement and virtual work, for each and every holonomic system, we are getting delta omega is equal to 0. So, this is the beauty of using virtual displacement. We do not have to worry about whether the system is scleronomic or rheonomic. If it is holonomic, we can always write delta W equal to 0. Great. So, now what do we do? So, we have understood, I hope you have understood this two terms, virtual displacement and virtual work. Now, let us move on from here and try to see where will this take us. Okay. So, you see, we first started this lecture, the previous lecture, by writing this equation f is equal to m r double dot, or rather we should not write m r double dot. In general, we should write p dot, right. Now, in order to and this is for a whole system. I can break it down into the system of particle formalism. For each particle, we can write pi dot. This is also valid. We can also put sum on both sides, which is essentially just another way of writing this equation. This is also valid. What we can also do is we can do fi minus pi dot, okay, sum over I is equal to 0. And also, because this quantity, this left hand side quantity will always give you will always be equal to 0, given that the system is in equilibrium. I mean, I should not say system is in equilibrium. What we are doing is we are just bringing everything into one side and writing this side equal to 0. So, this has to happen. It has to, I mean, this equation has to be satisfied, no question about it. So, as this has to be satisfied, what we can do is we can multiply for, I mean, this is valid in both forms, please understand this. This is valid in a summation form, also it is valid in individual form. If for an individual particle, I can write an equation which is, if I forget about the combined equation now, I can just concentrate on the individual equation, which is fi is equal to pi dot, right. So, this is valid for each individual particle in a system of particles, that we have seen when we discussed in the system of particles. So, we can manipulate it into this form. Also, now what we can do is, as this is equal to 0 for each of this particle individually, we can multiply this with a virtual displacement delta r I, and then it still remains equal to 0. Not only that, we can sum this over all the system of particles, starting from I equal to 1 to n, whatever be the number of system of particles, and we still get this equation, which is equal to 0. So, essentially what we did is we started from one particle equation, manipulated it, brought it both into the one side, set right hand side equal to 0, assuming that there is no other forces except or rather all the forces are included in this term, right. And then we just multiplied this with this one, forget about this, multiplied this with this one without losing any generality, and also summed over all. Now, each individual term in this summation is equal to 0, right. Now, and as each individual term is equal to 0, of course, the summation will be equal to 0. Now, please remember f I has two parts. One is f applied plus the other one is f constraint, and also we did that little bit. Replace it here. Okay. So, replace it here and you can write f I applied minus p I dot delta r I sum over all I is equal to 0. Because we have shown already that in case of virtual displacement, f I c dot delta r I will be equal to 0 for each individual i's. So, for each individual particle, if we are considering virtual displacement, the virtual displacement has to be, the work done due to virtual displacement has to be equal to 0 for each individual particle, that we have shown already, right, for any holonomic system. Please remember, all this formulation is for holonomic, right. Non-holonomic systems we will consider later. So, this is a relation which is a different form of Newtonian equation itself. Please remember, we always have to start from Newtonian equation, not that we are developing a new physics altogether. It is that simply that we are starting from Newtonian mechanics, trying to manipulate mathematically the same. I mean, basically right now what we are doing is pure mathematical manipulation, and we are trying to see if there is any advantage of writing Newtonian equation which started off in this particular form in this particular form. Is there any advantage? Okay. It turns out there is an advantage. The advantage is, here we have already found out the work done due to forces of constraint. I should write a C here, okay. And as this is always equal to 0, we have subtracted this from this equation. So, this equation is free from any force of constraint. F A is the applied force. So, whatever forces we have applied on the system, we will consider only those, okay. And this principle has a name, and this is called D'Alembert's principle, okay. Now, this D'Alembert's principle gives you one advantage. That advantage is, it has removed all the forces of constraint from the system. It also gives you one disadvantage. What is the disadvantage? Recall that for Newtonian mechanics or Newtonian equations, let us say you have particular form of equation which is F equal to, for I am not writing it for individual particle, but writing the equation for a rigid body. Let us say F equal to m r double dot, right. Now, let us say you are working on a Cartesian coordinate system, and you know each components of forces individually. So, you know f x, f y, f z. So, what you can do is, you can break this equation into this simple, so not exactly simple, but these three equations, and m z double dot is equal to f z. You can do that. Of course, whether it will be integrable easily or not, that is a different question altogether. We are not going into that question at all, whether it will be integrable, whether it will be difficult to solve, but at least you can decompose it into each individual part, and assuming that these forces are independent of each other, that means x force depends only on x component, not y or z component, you can always, in principle, you can always integrate this, and you can essentially get x and y and z as a function of time. So, starting from Newtonian equation, you can get individual equations for individual components, but starting from D'Alembert's principle, you have to understand that this is a single equation. There is no breaking it into component thing. Why not? Because although we have removed the forces of constraints, we are still working in with number of coordinates which are essentially the number of coordinates required to describe the whole system. Let me elaborate. Assuming that we have a n particle system, how many coordinates do we need? We need 3n numbers, right. And this r i's, please remember that when we are writing it into component form, it is a vector notation. So, each of these vector component essentially can be broken into 3 components, right. So, we have, if the summation runs from 1 to n, we have altogether 3n number of such components, because for each of this vector we have 3 scalar components. So, altogether we have 3n numbers of r i's. or I mean, so what we are doing here slowly we are adapting a notation where instead of writing x1, y1, z1, yeah, or rather instead of writing x, y and z components of each individually, what we can do is, so whether we can write x1, y1, z1, x2, y2, z2, so things like that, or what we can do is we can just write x1, x2, x3, x4, x5, x6. So, we will be using this explicitly. So, if we have 3n number of total coordinates needed, if we have n particles, we know we need 3n number of coordinates, then we will just use x1, x2, x3 up to x3n. Okay. So, what we are going to do is, instead of writing vector equations, we will just reduce this equation into scalar and we will sum it from I equal to 1 to 3n. This makes more sense and we will be using this notation uniformly from now onwards. Unless otherwise specified, this index runs over all required coordinates, right. So, we have 3n number of coordinates to begin with. Now, out of this 3n, how many are independent coordinates? Please recall that if you have an equation of like C1 x1 or polynomial or rather linear equation of the form C1 x1 plus C2 x2 plus C3 x3, okay, plus C4 x4 equal to 0, and if and only if your x1, x2, x3 up to xn, they are all independent, only if all these are independent coordinates, then and only then you can say this equation implies C1, C2, Cn equal to 0. What I am trying to tell you is a polynomial, I mean linear, so this is a very basic condition for linear dependence and linear independence in your linear mathematical methods course. I am pretty sure you already know how to define a linearly independent system of coordinates, linearly independent system of coordinates. What we are trying to tell you that although we have 3n number of coordinates, this 3n number of coordinates are not independent, right, because it is not a, I mean the system is not free. System has n particles which needs 3n number of coordinates, but at the same time system has k number of constraints. So, this k number of constraints means we need 3n minus k number of independent coordinates. Okay. This we have discussed already, but this formulation breaks when we are discussing a rigid body. Frankly, this I mean why it happens, because n and k both approaches infinity there. So, this relation is not valid anymore, but in general for a system of particles where this number n and k they are both finite, we can always write that total number of independent coordinate for a system with which has n particle, that means 3n number of coordinates and we have k constraints. So, the total number of independent coordinate will be 3n minus k. Okay. Okay. So, now we have a situation, we have an equation which looks something like this, okay, but we cannot say that all the coefficients are individually 0. That means, I cannot say that for each pair, I mean each particle f I a minus p I is equal to 0, not that. The whole thing is 0, but not the individual coefficients. Let us say these are your x1, x2, x3, xn like this, and these are your C1, C2, C3. So, this is your Ci term and this is your Xi term. So, because xi's are not independent, as if as in this equation, only if they are independent we can claim that all ci's are individually 0. Similarly, if they are not independent, we cannot say that this term is individually 0, the whole sum might be 0. So, there is a problem. What do we need in order to circumvent this problem? We need something called generalized coordinate. How many generalized coordinate do we need? We need 3n minus k numbers of generalized coordinates, and these generalized coordinates, okay. So, these coordinates actually need not be coordinates as a whole. What I am trying to tell you that it could be electric charge, it could be mass, it could be some independent quantity which is not dependent on any other quantity which is used to describe the system. So, in order to, what I am trying to tell you is, we need, for a system with n particles and k number of constraints, we need 3n minus k number of independent parameters, that just to say, and all these parameters, they might not have the dimension of length typically, or angle, for example. It could have, it could be electric charge, it could be electric current, it could be mass, it could be what else it could be, it could be a field it also. So, there are many examples, we will deal with some of these examples. Now, if I can somehow reduce this equation to in terms of generalized coordinates, then I can individually set all the coefficients to equal to 0. What I am trying to tell you that, let us say there are 3n minus k number of coordinates. Let us call this number so we call them q1, q2, q3 up to qn. Okay. Let us call this number small n, right. So, these are the independent coordinates. Now, they are not, it not that there has to be some connection, right. We cannot just define this q1, q2, q3, qn's just like that. I cannot just say, okay, this is one coordinate, that is one coordinate. There has to be some relation with the existing non-independent coordinate system. So, let us assume these are our orthogonal coordinate systems, either spherical polar or standard orthogonal coordinate, any of this. And we want to move into an independent set of coordinates, where a set of coordinates which is at par with the number of independent coordinate required, and they are given by this. There has to be some sort of transformation equation which says R1 is function of q1, q2, qn, R2 is a function of q1, q2, qn, and similarly R3n is also a function of q1, q2, qn, right. There has to be a relation. Let us assume that, take an example, we discuss central forces. Central forces means we need two coordinates, right. We see that their system has, which is moving, I can show you systematically, we will do that later, which is moving in a circle, in a planar orbit, basically has 2 degrees of freedom, and that is pretty obvious from the way we look at a system. And essentially we have chosen r and theta. Now, initially if we consider free particle in a 3D space, we need x and y and z. So, there must be some connection between x, y, z and r and theta, right. And we know how these equations are. There are transformation equations that we can always write x equal to r cos theta, y equal to r sin theta. Okay. And of course, right now we are not considering z, but so our z is always equal to 0, but this is also an equation, right. So, that way these are the transformation equations we are talking about here. Similarly, we can have reverse transformation equations. We can express this q1 in terms of r1, r2, r3 up to rn, q2 in terms of R, all the R's like that. So, there is a set of transformation and reverse transformation exists, which connects between the standard orthogonal coordinates with the generalized coordinate. That relation has to be there. I am not saying that it is important to have a dimension of length or angle for this q1s and q2s, but there has to be some relation. They cannot be just totally disconnected. Okay? This relation is very important. Now, it turns out that D'Alembert's principle, although they are not independent of each other, so we cannot equally, we can equate this coefficient to 0, but what we can do is we can still use D'Alembert's principle in order to solve simple problems. Now, let us take an example. I will end this lecture with this. So, right now please remember we are working in the dependent coordinate system. Okay? Before going into generalized coordinate, we are working in the dependent coordinate system. So, let us assume we have a simple pendulum, right. Again the simple example, it is hanging there is a length L, right. Now, can I write the simple pendulum equation in D'Alembert's notation? It turns out that we can, of course. We have a constraint equation, let us say this is my x axis and this is my z axis. So, x square plus z square is equal to L square, and if I now write the individual equations, what are the applied forces? So, applied force is mg and which is towards z direction, is not it? So, what we can do is we can write the D'Alembert's principle like this. So, it will be mg for the x component f along x component is equal to 0. So, we can write minus m x double dot delta x plus for the z component it will be mg minus m z double dot delta z, which is equal to 0, right. Now, in this particular form, this is what we get from D'Alembert's principle. It is not extremely helpful, but what we can do is we can use this equation and we can reduce this x delta x plus z delta z is equal to 0, and this readily gives you delta x is equal to minus z delta z by x. So, what we are doing is, as it is, D'Alembert's principle is not very helpful, frankly. D'Alembert's principle, just like this, we can write a long equation which has all the terms in it. If we have, so if we consider a spherical pendulum, we can do that. In spherical pendulum, we have to take another term which will have an y displacement as well. Okay. Now, but it is not very helpful, but when we are using this constraint condition, and please remember that delta and d has similar properties when it comes for standard differential operation. It is just a differential, but it is a virtual differential, because in a sense that if we anywhere if we encounter a delta t, we uniformly put it equal to, unanimously put it equal to 0. So, delta t is always equal to 0. Okay. Keep that in mind and just apply any standard normal derivative operation. When we are using virtual displacement, just use it as if it is a normal derivative, plus please make sure that whenever you see an delta t, put that equal to 0. So, we do that, and once we do that, we substitute this for delta x, we see minus m x double dot z by x plus mg minus mz double dot. Of course, m can also be taken out of the system, right. Delta z is equal to 0. Now, if this is the case, we can safely say delta z, we can safely equate this whole thing is equal to 0, because now it is single parameter. We do not have an equation where we have both delta x and delta z. We have reduced it to a single equation with delta z, and delta z and the coefficient of that can easily be equated to 0. If we do that, equate this equal to 0, right. So, what do we get? Minus g z double dot is equal to 0. Now, we have to assume, we have to make this standard assumption that it is a, I mean, if we now want to see that the, if we want to reduce it to our standard equation for simple pendulum, we have to assume that the displacement is small such that z double dot is equal to 0 and z is approximately equal to L, the length. That means, the displacement is so small that the velocity in the z direction is almost negligible, or acceleration in the z direction is almost negligible, and the length z is almost equal to L. So, if we put that here, what do we get? We will get minus x double dot x double dot is equal to g by L x, and there should be a that we can always check. Okay. So, anyway, so you will get this equation, or there should be a minus sign here, you have to check the steps, you can do that. So, finally, we will get back this equation if you make this assumption, which is okay. So, you see D'Alembert's principle, although as it is not very useful, we can always use the forces of constraint to construct an useful equation out of it. Also, there is another way of doing it. We can also use the force of constraints in a slightly different way. We will do that in the next class. So, for now, I will just summarize what we have learned in this class, in this lecture. First is, we have seen that virtual displacement can always be used in order to make the virtual work done equal to 0, even for even for rheonomics constraints. Secondly, we can write Newton's equation without involving the forces of constraint in this particular form. Then this can be used along with the constraint condition to get the standard differential equation in Newtonian form, right. What I mean is, the same equation we can get in the Newtonian mechanism also, but we have to consider this tension T, right. So, we are not bothered about this T anymore, but we can still get this familiar equation. And also, we defined some quantity which are called generalized coordinates, which the number of generalized coordinates should be 3n minus k, which is the number of independent coordinates required, and these generalized coordinates are related to the standard Cartesian coordinates by this type of transformation equations. So, right now we have to stop here. Probably in the next lecture we will be able to derive the Lagrangian equation of first kind and second kind. Till then, thank you.